Okay, so off we go. So real quick, the first thing I need to say, kind of for legal reasons, we are recording. Y'all saw in the video that I sent out this weekend that I record all of my lectures and post them to the YouTube channel. So the way the audio works is it's recording right off of my laptop. So the radius is pretty small, but just in case, just be warned, if you ask a question, it's possible your voice might be picked up by the recording, so you've been officially notified. Okay, all right, so I'm not going to go through all this stuff again. Y'all already watched that video, and that's good enough. But I just want to draw focus again to this bit right here. It's so important. This course is about ideas and reasoning. Right, so it's a huge part of every aspect of the course. You're going to notice that starting today with the lectures. I'm going to talk a lot about ideas, right? And I'm going to talk a lot about reasoning, right? And you're going to see that in continued lectures throughout the term. You're going to see that on the exams. You're going to notice that on how grading is done. It's all about what can you show me that you understand, right? Ideas and reasoning. And it's not about the answer at the bottom of the page. Okay, I'm not going to repeat that whole spiel again. That said, let's move on to this, what I call the introduction. So, why are we here? Why are we taking this class? Right, pretty big question. We should probably have a good handle on that. And I know the answer for many of you is because my major requires it. Okay, right, so fine. So why does your major require that you take multivariable calculus? Okay, I'm hoping that y'all are already sold on this point, that single variable calculus is really important. I mean, y'all have taken at least 2 semesters of single variable calculus. You've seen a bazillion examples of real-world practical scenario kinds of questions that you can answer with single variable calculus. Specifically, derivatives and integrals. Well, why derivatives? Because derivatives keep track and allow you to get your hands on how things change. The world's full of stuff that's changing. In fact, most things in the world change in some sense. Right? So that's obviously important. Integrals, commonly misunderstood as addressing the question of area under a curve. It's really not the point. It's kind of a curious, convenient example, I would say. Integrals are about accumulating quantities and how to compute those accumulating quantities. And I'll talk more later about exactly what I mean by this. But roughly speaking, anything where you can chop it up into little pieces and then add up to get the total, which is a lot of things, right? So, again, the world's full of stuff like this. And you've again seen some examples. So let's address, though, the obvious nagging point here that the world is 3-dimensional, not 1-dimensional. Right? So if you think about it, one variable, right, is not going to do a good job in general of addressing a 3-dimensional world. And frankly, that's just one example of why we need multivariable calculus. There is much more, and I'm going to show you an example that I'm alluding to here in just a moment. So first, some easy, obvious, low-hanging fruit examples. Let's look at this first one right here. Suppose we have temperature as a function of position, and this being a function, this being position in space, so x, y, and z. So let's imagine this room right here. Right? The temperature is not constant. The temperature in that corner over there is not the same as the temperature right up next to that light bulb right there. So temperature depends on location by quite a bit and is a function, therefore, of x, y, and z. Okay, well, with that in mind, if I'm here and if I'm moving with some velocity, temperature is going to be changing as I move with that velocity. How am I going to get my hands on the question of how fast the temperature is changing? Well, I can't just, view temperature as a position, as a function of just x, the x coordinate of position, because it's not just a function of x. And I'm also not just moving in the x direction. I might be moving somewhat in the x direction, but I'm moving in the y direction too, and the z direction too, and it's at some sort of a weird angle. Are we going to have to do some trig here? Or, I mean, it's how do you deal with this, right? Really not obvious. And it turns out that this is something that multivariable calculus addresses very nicely. So anyway, like I say, this is the obvious low-hanging fruit of why it matters that we live in a three-dimensional world, and why that means single variable calculus just isn't going to cut it for a lot of purposes. Here's another one, integral example. Let's suppose you have some lump of stuff, and suppose the density is not constant. Sure, we've seen a million examples, this kind of thing. But in particular, let's suppose that the density depends on all three coordinates of position. Now, what y'all have seen before in Calc 1 and Calc 2 classes are where, like, if you look at a slice, then the density is constant on that slice. Well, that's a wildly unrealistic assumption in most cases. Right? So if that is the case, if density is a function of just one single variable and it's therefore constant on slices, then yeah, you cut it up into a little sort of coin-shaped slices, and you say density times volume gives you mass on those little slices, and then you add up over all the slices. Y'all have seen that, again a bunch of times. But if it's not a function of a single variable, then when you look at those slices, density's still not constant. So you're dead in the water. You got nowhere to go. Right? And so single variable calculus, again, does not cut it here. So we're going to have to figure out how can we take, and we're going to try to rip off the main idea of single variable integration and try to come up with some sort of an analogous way to do multivariable integration in a way that would actually allow us to answer a question like this. And again, much more real world, much more sort of natural. All right. Okay, now that's these are kind of broad, like I like to call them low-hanging fruit, as sort of obvious, seemingly simple though kind of examples. I want to show you all some that are field specific. So there are many different applications in many different fields. So let's start with econ, just because, and I think some of y'all might be econ majors, maybe, possibly, doesn't matter. Anyway, here we are. So here's what an economic model looks like very often. Now, I just made up this equation. The specifics aren't the point here. But in practice, very often, when you have a bunch of economic quantities, you don't just write down immediately, for example, P equals, some function of the other variables. That's just not how the models tend to work. Very often what you can do is you can argue that, look, this represents one certain aspect of the problem, this represents another aspect of the problem, et cetera, et cetera. And these are all the different aspects of the situation, and we know, again, depends on your economic model, depends on the situation, you might know that those have to add up to either zero or a constant or whatever. So you write down economic models. Again, they tend not to be functions. They tend to be just some random equation in which you can't really solve necessarily for anything. Okay, well, so again, pretty realistic real-world scenario. Let's suppose I know how some of these variables are changing. And now let's think this through for a second. If L is changing, that value is changing, this term is changing, oh, wait a minute, but the total has to stay at zero. And then maybe some of these other variables are also changing. Everything in this equation on the left-hand side is changing. How could it stay constant at zero? And the answer is because P is going to have to change also. Right? And if you tweak all the other variables other than P, there should be some way to tweak P also under certain conditions that makes the balance maintained. Right? And so reasonable question, when you know how these variables are changing, how do you figure out, correspondingly, how much P changes? So this is a very natural scenario, right? Economic model, stuff's changing. I want to know what happens as a result. How do we answer this question? Well, short answer, multivariable calculus, right? So this is one of the things that we're going to study. This is a topic that's on our syllabus and that we will be covering. Okay. All right. So, for example, this is why econ majors should take this class. Now, real quick, I pointed out that this alone up here is not the only reason that we need multivariable calculus. The fact that we live in a three-dimensional world is a reason that we need multivariable calculus. It's not the only reason. A lot of people misconclude, in my opinion, that, well, we live in a three-dimensional world, so we really only need three-dimensional multivariable calculus. Anything above 3 dimensions, well, that's crazy theoretical nonsense that doesn't have anything to do with the real world. So it might seem. And I beg to differ. Check this out. We have 6 variables in this economic model here. We are doing math in 6 dimensions. It's kind of a creepy thought. Right? But anyway, so this idea that, you never need to go above 3 dimensions. Nonsense. Of course you do. Right? And you can imagine similar examples in, engineering. You're going to design some sort of a car engine or something like that. And, well, there's a bazillion parameters that go into the design of the engine, right? So you could easily be doing 20-dimensional math. It's very real world. Nothing abstruse, abstract, implausible about any of that. How are we doing? Everybody with me? All right. Now here's the good news. I'm not going to make y'all do any visualization above 3 dimensions because, frankly, I don't believe it's possible. There were rumors about this one guy, years and years ago, and the theorems that he came up with that were, took place in 4 dimensions, were so amazing that there was this rumor. I think he's a 4-dimensional alien, and he could actually visualize it. Probably, he was just really good. He was a really good mathematician. Nobody, I'm pretty sure, can actually visualize above 3 dimensions. So that's not the point here. The point is that we need to have the equations. We need to be able to actually do the analysis in greater than 3 dimensions. And so that's why I'm going to be, keeping my stuff general as opposed to always tailoring it to 2 and 3. Okay. All right. Okay, some of y'all may be engineers. I'm guessing quite a few of you. Possibly a physicist or 2 as well. So here's some equations that y'all are going to see tons of. These are called Maxwell's equations. There's what we call 4 equations here. These are actually extremely closely related equations. I know they don't look like it at a glance, but they are basically the same thing. And we'll talk more about that later on when we get to chapter 7. But anyway, so we call these one equation, and thus Maxwell's equations is 4 equations. So a lot of questions to ask about this. For example, what does that mean? I mean, we can break it down to the simple matter of what does that symbol mean, right? What does that symbol mean? So, of course, we're going to have to know that. But then also, what is this as an equation? What is that actually saying, right? What do these constructions talk about? Next reasonable question, how can you best understand this equation? How do you know it's true? Aside from maybe you're willing to believe me, right? Which, by the way, is not how math is done. Math is not done by authority. Right? So, on some level, I want y'all to try to I want you to be able to persuade yourself that this is true. maybe not rigorously, right? But I want y'all to have a good intuitive understanding of the ideas that will allow you to, make a reasonable case for why I'm going to say this should be true. The formalities and the particulars are not important. Okay. And then, what does this statement tell me, for example, about electric fields? And it turns out that, in fact, that statement tells us something tremendously powerful and important for understanding physics about what is the nature of an electric field. And so that's another thing that we want to make sure that we understand. So notice what we're talking about here is not, I want you to memorize the formula, or I want you to be able to plug and chug with the formula, right? We're going to be talking about the ideas. Okay? So anyway, multivariable calculus is kind of the answer to all of these questions that I'm pointing out here. And so understanding multivariable calculus will help you understand physics way better. Right? You take away multivariable calculus, and this is all just kind of mysterious nonsense. Okay. All right. And likewise with the others. Okay. Schrodinger's equation. This is quantum mechanics. And those of you who are chemistry majors will have some use for this. Now, why is that? I mean, why do chemists need to understand Schrodinger's equation at least a little bit? And by the way, chemistry majors will take a class called physical chemistry, PChem, right? In which you will study this somewhat. The answer is chemistry is about molecular bonds. I think that's a pretty easy pitch. Molecular bonds basically come from the behavior of electrons. That's just how that works. And how do electrons obey? Well, they obey Schrodinger's equation. So this is very fundamental in really, if you get right down to it, how does chemistry work? So, okay, what's the deal with Schrodinger's equation? And one of the hardest parts of it is this thing right here, and that is an object of multivariable calculus. And again, we'll be talking about that. The good news for y'all, we're not actually going to be doing Schrodinger's equation in this class, but this guy here, this operator, is something that we are going to talk about. So that'll help you when you do get to the stage of dealing with it. Physicists, by the way, you will 100% be doing legit, full-on, full-strength calculations with Schrodinger's equation. So it's going to be super important for y'all. Okay. All righty. How we doing? Is everybody on board? All right. So there's a lot more. I picked these because these are kind of the coolest, most important in some sense examples that occurred to me as I was writing these notes. But this is not the list, right? There's a lot more. My point to these examples is multivariable calculus is bonkers important in a lot of different fields. So my little summary statement, I think this is actually nice and pithy. Multivariable calculus is the calculus of the real world. Recognizing that the world is multiple dimensional, recognizing that systems tend to involve multiple variables. If you're going to do calculus, realistically, most of the time it's going to be multivariable calculus. Okay. Right. So now on to the actual syllabus content of the course. Real quick, I'm going to point out that one of the prerequisites for this course is linear algebra. Presumably y'all have all had a course in linear algebra. I hope that that's reasonably fresh in your minds. I know it's, we've got a summer in between that and this, so maybe it's been a while. But do make sure that you kind of brush up on the I'm going to say the basics. I don't have any plans to use any Jordan canonical form in this class, as I think I noted in the lecture and the recording I sent this weekend. So nothing far out, right? But just the basics of linear algebra, you need to be strong with that because we are going to use that quite a bit. Now, chapter 1 here is largely about arguably, I don't know, 2/3 of it, 3/4 of it, it's pretty much linear algebra. Right? So I'm going to do a lot of skipping in this chapter, and I'm going to also do a lot of moving super fast through this chapter. So keep in mind, as I mentioned in the recording, I have to make these terrible, tough choices. I don't have enough time. I can't cover everything. Not possible. Can't be done. So I've got to make these tough choices of, okay, what am I going to simply not talk about? I hate that. I would love if this were a full year course, and then I wouldn't have to make those tough choices. I could just do everything. But that's not how it works. So I am going to move really quickly through this material. Hopefully a lot of this is review, and therefore, it's just a matter of brushing up. Some of the other of this stuff that I'm going to be moving really quickly through follows pretty immediately, with not too much trouble from things that you've seen before. And so given that we've got a lot of this near the end of the semester that we really need to spend time on and really need to be able to focus and dwell. I need to move quickly through the relatively light stuff. So, okay, here we go. Also, real quick observation. I'm going to start with section 1.6. 1.6 has the sort of most purely prerequisite material in all of chapter 1. Yeah.
Quick question. Is that supposed to be less than or equal to sign, or is that some sign that I don't know?
You're talking about this right here?
Yes.
Yeah, that's less than or equal.
Okay.
I'm sure that any criticisms of my handwriting are valid.
Just wanted to make sure it wasn't some symbol I didn't know.
No, that's just less than or equal.
Okay.
Yep, absolutely. Right. Good question. Thank you for that. So starting with 1.6, again, make sure to review your linear algebra. I'm going to assume that you're good to go with all of the, again, what I'm going to call the basics. And real quick, the triangle inequality, and I kind of hit the highlights of this on the recording I sent Saturday, but the magnitude of A in this picture is that length, and the magnitude of B in this picture is that length, and the magnitude of the sum is that length. And basically what this is saying then is that purple is less than blue plus green. Well, of course it is. I mean, look at these 2 points. The shortest distance between 2 points is a straight line, right? That's an old satisfying result. And, well, therefore, this purple distance, being the straight line, that is the shortest distance. Thus, triangle inequality. Pretty easy to buy, I think. Okay. All right. Okay, here's one that you may have seen. I don't know if it was hit hard enough to suit my preferences, so I'm going to hit it again. This is how to do a matrix vector product, how to multiply a matrix times a vector. And I know you all seen the formula. It's the kind of dot products of the rows of the matrix, right, with the column vector. Okay, so that's one way to do it. And if your goal is the answer, then that's good enough. But that's not what this course is about. You're going to hear me say that 1,000,000 times through this semester. That's not what this course is about. So we're interested in ideas, and this formula right here is a really powerful idea for how to compute a matrix vector product. So this right here, matrix times vector. And just to highlight the phrasing here, first of all, it's a linear combination. You see right there, it's a linear combination. It's a linear combination specifically of the columns of the matrix. These vectors that we're taking linear combination of there, you can see right here, they are the columns of our matrix. Right? And then specifically, we use the coordinates of the vector as our coefficients in that linear combination. So I think this rolls off the tongue pretty nicely. A matrix vector product is a linear combination of the columns using the vectors as the coefficients. And it's a really nice way to think about matrix vector multiplication. Now again, from the point of view of the answer, right, to the turn the crank, plug and chug aspect, is this how I want you to, in practice, execute a numerical computation? No, probably not. Right? That dot product formula is super handy. Right? It's very convenient. But again, ideas, not answers. Notice that what we have here is a pretty cool connection between some otherwise not immediately clearly related ideas. This product, this, what I have in purple here, AX, is a linear combination of the column vectors. That is not at all clear from that dot product point of view. Right? Well, that's a neat fact. There are situations where that fact alone is good enough for all you need. So, very nice to have points of view on things that relate what you're talking about to different aspects of the question. This particular point of view is very nice in multivariable calculus. We're going to use this here and there, and so I think it's important that like I said, hit it again to make sure that everybody's comfortable seeing this point of view. All right. Moving along. Linearity. Linear algebra is about linear functions, and this is what that means. This is the linearity condition. And there's some equivalent formulations that are convenient in certain circumstances, but I like to focus on this one. A little easier to work with in most cases. This is our linearity condition. So the way I like to think about this is that if you have a linear combination of inputs, and let me highlight this a different way. If you have a linear combination of inputs, the result, when you put it into the function, is that same linear combination of the outputs. Or said differently, you can do linear combinations either before the function or after the function. Sometimes people say a linear function commutes with linear combinations. It's a very common phrase. So anyway, that's what linearity is. Important to make sure that you are clear on, when you see that word, that is the precise interpretation that they're talking about. And there's, of course, also, geometric interpretations. What is this? How does this manifest, visually? Right? And that's another important thing to understand. Again, think back to your linear algebra class. We can't review a whole linear algebra class, of course. All right, so some nice examples. This right here, nice example. A lot of people abbreviate this example as dot products are linear. So let me explain that terminology, calling this dot products are linear. If you look at this function that we're calling p, and look at what that function does to a given input vector x. Well, what is happening to this input vector x? Well, what's happening is it's being dotted with some given vector a. Right? So this thing that I'm claiming is linear, p, that I claim is linear, p represents the action of doing a dot product. So when we say p is linear, again, a nice little abbreviation is to say the dot product, with a fixed given constant vector a, of course. Dot product is linear. What do you think? Ready to buy it? Okay, now, that's the interpretation of this statement. How do we know this statement is true? Well, reminder, this word linear means that condition right there. Right? So if you want to check that P actually is linear, you're going to take this formula and you're going to plug it in to that condition and just see if it works. I mean, compute the left, compute the right. Do you get the same thing or not? Right? How are you going to tell? Well, the left side of the equation and the right side of the equation are obviously going to have a bunch of dot products in there, and y'all know already a bunch of properties of dot products. right? Kind of a big deal in linear algebra. And so just use your existing knowledge of the properties of dot product and simplify the left side, simplify the right side, and confirm that, yep, sure enough, they're the same and therefore linear. Yeah?
What's it called? In linear algebra,
Yeah.
I was taught about, what's it called, inner products.
Yes.
Synonymous with dot products, or?
Kind of, sort of. So inner product is a general construction that applies to any what we call inner product space. And an inner product space, it's kind of a vector space, but where you have this additional operation called the inner product, right? Now, the model that they used to come up with this idea of an inner product space is literally the dot product, right? So basically, people were looking at Rn and the dot product, and we're like, okay, what else can we find that kind of behaves analogously to Rn and analogously to the dot product? And anything that, in a lot of details to be written down, of course, but anything that behaves kind of like that we call an inner product. So dot product is an inner product. I would call dot product the model for all inner products. But it is just one example of an inner product. Yeah. Anybody else? All right. Okay, another example, and this is highly analogous, so I'm not going to spend any time on it, but as you might guess, I'm going to casually refer to this as saying that cross products are linear. And you can think through the terminology, why we would phrase it that way. And then next question, how would you show that cross products are linear? Well, again, plug into the linearity condition. Make sure it works. You all already know properties of the cross product, and you just have to, again, compute both sides. Make sure it works. Okay, this next one, and I waved my hands at this in the recording I sent y'all this weekend. This appears at a casual and careless glance to be saying that determinant is linear, but it's not. This is not saying that determinant is linear. It's a very important distinction. In fact, determinant is not linear. Easy counterexamples. By the way, as a nice little exercise, if you want to, try to come up with an example of why determinant is not linear. And the big point here to keep in mind is that determinant is a function that takes as its input an entire matrix. If you add two matrices, the determinants just don't add. Just don't. And so easy counterexamples. So now, why is that not what we're talking about here? Well, if you look carefully at this function that I'm calling d, what does d do? D takes as its input a single vector x. D takes as its input just this bottom row right there. And what is it that D does? Well, conveniently, we've got, I've got a formula for D right there, right? So apparently what D does is everything else in this equation that then subsequently happens to x. So D, capital D, says take your input, whatever it is, called x, make that the bottom row. Apparently we're going to need to know some given other vectors here, right? Stack those on top of your x to make a square matrix, and then once you have a square matrix, you'll then take the determinant of that. So the point is, what D is doing is not just determinant. D is taking a vector and then making a matrix out of it and then taking the determinant. Yeah? Okay. And the claim here is that this D is linear. And that's a really cool fact. Y'all may have seen this in your linear algebra classes referred to as multilinearity. And that's a nice way to think about this fact. Multilinearity is a recognition that it's not just the bottom row that makes this work. I hope you all might recall. But you can do cool linearity arguments not just in the bottom row, but in any row, as long as all the other rows stay constant. And furthermore, any column. Right. So anyway, this is called multilinearity, and that terminology doesn't get used in every linear algebra class, but I feel like it should. It's very handy. It's very convenient. It's a very cool fact about matrices, if nothing else, and in particular about determinants. Okay. All right. Okay. Yeah. The relationship between linearity and matrices. This is super, super duper important. We're going to be using this a lot. You want to make extra sure that you're good to go with this. And roughly speaking, what this is saying is that linear transformations are matrices. Every linear transformation is a matrix. Every matrix is a linear transformation. That's the sloppy way to say it. To be clear, I do have to restrict our attention to what I'm going to call Euclidean linear transformations. So by Euclidean, I mean the domain for the function has to be Rn. It can't be some wacky vector space like the vector space of all solutions to this homogeneous differential equation or something like that. No infinite dimensional vector spaces, nothing like that, right? So Rn as your domain, Rm as your target, then every such linear transformation can be represented by a matrix in this sense right here, defining T as a matrix vector product. So really cool fact, really important fact. How do you prove this? I'm going to leave the details for y'all to read on your own. Y'all have presumably seen this previously, but this is the good part right here. Let me zoom in a little bit more. The key insight, and I did not figure this out on my own. Somebody showed this to me. I emphasize, right? Don't think to yourself, man, I never would have figured that out. Yeah, me neither. Right? Somebody showed this to me. Math is this wonderful example of basically everybody taking advantage of the great ideas of those who came before them, right? So I'm copying people who were copying people who were copying, the originators. But here's the key idea is this right here. Start with your standard basis vectors. That's like IJK. Y'all remember standard basis vectors? I hope, yeah. Okay. Take your standard basis vectors, ones and zeros. Do your linear transformation to them, whatever that T is. Do the linear transformation to those standard basis vectors, and whatever you get, as a result, make those the columns of your matrix, and it'll just work. This is the magic trick. Whatever your linear transformation is, apply it to the standard basis vectors, make those the columns, and that is the magic matrix that will execute your linear transformation for all vectors. And the argument here is pretty straightforward and a pretty clear read. I'm going to let y'all read through that. And again, please do take the time and look through. Again, this is all linear algebra. It's all review. But make sure that you're good with all the steps through that process. And notice we do get the desired result. The claim was that we can find a matrix that makes T of x equal to AX. And as required, T of x indeed is AX. All right. So let me tell you in practice how we're going to be using this. I made a reference during that recording that I sent this weekend to, you need to know how to write down, for example, rotation matrices. right? So if I say, I want the function that takes all vectors in R2 and rotates counterclockwise by 60 degrees around the origin. How would you find a matrix that will take any vector and rotate by 60 degrees counterclockwise around the origin? Well, the answer is to say, well, it's a linear transformation. I can take my standard basis vectors and there's only 2 of them. I can take my standard basis vectors and I can just straight up rotate them. Just do that rotation, do a little bit of trig and geometry, and I can write down exactly what those images are. And then I'm going to take those results, I'm going to make those my columns, and bam, that's my matrix. That's my rotation matrix. That looks familiar, I hope. So, make sure you're good with this. If you are good with this, great, super. If you're a little shaky, maybe, and not 100% clear what's happening here, you've got a bunch of options. Talk to a friend. It's an easy way to do it. By the way, they might not know either. Now you have a collaborator. Try to help you. Between the 2 of you can try to figure out what's going on here. You can go to the help room. Right? The help room is a great resource. It's open like 9 hours a week, or so. It's really awesome. It's like free tutoring, right? They just show up, no appointment necessary. So great resource there. Of course, my office hours. You're very warmly invited to my office hours, and by the way, also to the other professor. He has office hours as well, and we do an office hours sharing thing. So if my hours don't work for you, cool, go to his. Right? And we'll be happy to help you make sense out of this and make sure that you're good to go with writing down, rotation matrices and reflection matrices, things like that. All right. Okay. Let's see here. Okay, I'm doing fine. Before we go on to the next thing, I like to throw a minute or 2 to talk about this fact. I think this is underappreciated. Again, I know y'all all know how to multiply matrices. What I wonder is, do you know why that kind of weird formula, if you really think about it? Why is that the formula that we use to multiply matrices? When I first saw that formula, I thought, well, that's super weird, right? So why? Who dreamed that up? Why are we all following that same? Somebody came up with a weird idea and everybody's just doing it? No, there's a good reason. Right? And there's different points of view on what that reason is. Lots of different points of view you can take. This is my favorite, and that is if you have 2 matrices. Again, keep in mind each matrix you can think of as a linear transformation. Right? The act of multiplying the matrices corresponds perfectly with the act of composing those linear transformations. Right? And this is what I'm going to call mathematically natural composition. Right? You've got a function that has inputs and outputs, and you take what comes out of the one and you put it into the other. It's just like putting Legos together. Right? There's a very, very natural mathematical construction. Composition, again, it's just very natural. So matrix multiplication is what it is so that it will represent that composition, that very natural process of composition. That's why we multiply matrices by that weird formula. Is that satisfying? All right. Okay, moving along. Okay, so we finished 1.6. Let's see here. I'm going to say just a couple of things about section 1.1. Very little needs to get said. It's almost all review. But it just kind of bugs me that the book uses bold. as the sort of typographical indicator that it's a vector, not a scalar, because it's really hard for us working with a pen or a pencil or a stylus, right? To sit there and, I mean, it takes 5 seconds to write a letter in bold, right? It's silly. There's a very convenient alternative that's also very standard. You put a little arrow over the letter, and that also just as well. That's fine. Indicates that this is a vector, and it's of course in handwriting, basically instantaneous. So anyway, that's my little quibble. Our textbook uses bold. Show-offs. But I'm going to use the vector hats. Okay, my other little quibble is to the question of how we would represent this vector. Here, we've got 2 points, P1 and P2. How do I write that vector? And I think it's a pretty easy pitch as to why they might want to write it like this. Right? Because after all, it starts at P1, it ends at P2, so boom, right? It seems perfectly reasonable. Okay, true. But here's the thing. P2 is a point, well, sure, but every point can also be thought of as a vector. That P2 is a vector. P1 is a point, but which means, of course, it can also be thought of as a vector. And check it out. You remember how vector addition works. In fact, this purple vector is literally P2 minus P1. It's the thing that you add to P1 to get P2. So it's P2 minus P1. So now let's look at our options here. Now we have a choice. We can represent that purple vector. We can represent it like this, or we can represent it like this. And let's talk pros and cons. The pro of this is that it's, I'm going to say, syntactically pretty obvious. That's nice. It's also got one fewer stroke of the pen, right? I don't have to go to the great trouble of writing this little minus sign, I guess, right? So that's another advantage of this notation. But I think I can make a much stronger case for the advantages of this notation, and it goes as follows. Algebra is a good thing. Algebra is how we solve problems. Algebra is awesome. I want to show the algebra. I don't see any algebra in that notation. I'm hiding the algebra. Why in the world would we want to hide the algebra? Algebra is our friend. Algebra is a good thing. I like to write it in a way that makes the algebra visible because I like to be able to relate problems that I'm looking at to algebra so I can solve problems. So I basically universally use this notation right here. You may do as you will, but this is much more useful in practice, in my opinion. That makes sense to everybody? Okay. Any questions? How are we doing? Okay. Okay. So, by the way, that does it for section 1.1. So we've now got 2 sections down. Let's talk a little bit. We're not going to have time for much on this. Let's see how we're doing on. Not much time here. I'm just going to say something real quick, and that is just the broad stroke definition of a parameterization. By the way, parameterizations are going to be really important in this class. I'm introducing them early for 2 reasons. First of all, the book does. Second of all, it's good to have ideas available to stew in your minds before we really start using them a lot. And this is a little early in some sense, but again, that's a good thing. So what a parameterization is position as a function of, I'm going to say, time. Position as a function of time. Very natural, if you think about it. And you need to watch my fingertip here. As I move my fingertip around, at any given moment in time, there is a corresponding position. So the act of my moving my pen around gives position as a function of time. Or you might say, now if I, instead of my fingertip, if I were to take my stylus and do it on a piece of paper, I'm drawing a curve. And so the resulting curve we call a parametric curve. And the function that draws it we call a parameterization. So we're probably out of time now. So we'll draw the line right here. Picking up there then on Wednesday. Y'all have a good rest of your day. See you later. See you on Wednesday.